So I was talking last time about, again, probability. Theoretically, we were talking about a deck of cards, talking about 4 suits, 13 values each. And I said, okay, chance you get a queen is 1 in 13. Chance you get a red, 26 out of 52. And then I tried to draw my ideal Venn diagram, show a picture of what's going on here. But now I have 2 new options for the way I think of my probabilities. I want to try and figure out chance of getting a red card or a queen, chance of getting a red card and a queen. There are 26 red cards. There are 4 queens. The problem is where that question mark is in the Venn diagram. I need some names. So let's consider this section in our Venn diagram. If our 2 sets were just given arbitrary names, then that piece would be the overlap between them. And in set terms, we would call that the intersection. And the way I remember the symbol for this is I look at that lowercase n in the word and what we write is we write A, and then this upside down, well, it kind of looks like that lowercase n, B. And that means intersection. That goes with the word and. So tell me, in my 2 sets, queens and red cards, do we have an intersection? The queen of hearts and the queen of diamonds, there are 2 cards in between. So I can say, wait a minute, there are only 2 here. So this probability is 2 out of 52. Symbolically, or is not just this intersection, it's everything in both circles. So if I were to redraw this Venn diagram, again, labeling them A and B, if I covered everything, that's or. You're in the first circle? Yep. You're in the second circle? Yep. Those both work. Whether you're in one or in the other, I'm going to call that the union of A and B. And this upright U is going to be my symbol, A union B. So now let me see if I can go back up here and answer that first thing. What is the chance I get a red card or a queen? Oh, wait a minute, there were 4 queens. There were 26 red cards. So shouldn't I just get 30? I've already counted the 2 red queens. When I counted the red cards, I shouldn't count them again, right? And this is why I drew the circles as overlapping, because here I've got all my red cards. In the middle here, I have those 2 red queens. So when I count the queens, I double count those cards. And if I put them in twice, and I only want to count them once, I need to pull them back out. I've included them an extra time, so I need to exclude them. Called principle of inclusion and exclusion, but I remember it like this. The chance of an or is the chance of each one added together. But because I might have double counted something, I need to subtract off the chance in the intersection. So instead of being 30, it'll be 28. So in our case, the chance of red or queen is the chance of red plus the chance of queen minus the chance of both. So I always have to work out and before I work out or. Or if I'm going to work out or separately, I need to work out and as a result of that. I need to use this formula to find one from the other. Make sense? And also gets called the joint probability. Now, I'm going to make a statement. I want somebody to tell me why it's true. Chance of A and B must be less than or equal to the chance of A. The chance of A and B must be less than or equal to the chance of B. The answer is completely shown in the Venn diagram. Right?
Like the overlap between the two is always going to be smaller than this whole circle.
Unless
they're like completely overlapping.
Exactly. This little sliver in the middle can't ever be bigger than this circle, and it can't ever be bigger than this circle. So the number of things in the middle has to be less than or equal to the number of things in this circle. And then if I divide by the number of things in the sample space, that gives me these probabilities. Unless they overlap exactly the same, right? And then A and B are really the same set. We just thought of them in two different ways. Questions? Dice. I brought two dice, they're different colors. It's kind of hard to see, but the numbers are actually printed on the die, embossed on it. So, question. What is the chance I roll a 2 on this purple die? What's the chance I roll a 3 on this purple die? What's the chance I roll a 2 and a 3? If I try and do that in one roll, can you do that? Those two events have no outcomes in common. The only way you get a 2 on this, you get a 2 on this. The only way you get a 3 on this is to get a 3 on this. I only roll die one time. I can't do both. Events that are mutually exclusive are events that have no outcomes in common. Well, wait a second. That changes the picture in my Venn diagram. Here's my universe. I have an outcome, an event A. I have another event B. But they don't have any outcomes in common, means that the two sets don't overlap. In set terms, we call these disjoint sets. And we indicate that their intersection is empty. Now, because I'm a math geek, I use the empty set a lot. We have a symbol for the empty set. It's kind of like a Norwegian letter or a Greek lowercase letter phi. A lot of computer science people get really pissed off because they're told to write their zeros this way to differentiate between an O and a zero. That's our symbol for an empty set. So when I write this sentence, I can write A intersect B is an empty set. So the chance that my card is red is 26 out of 52. What's the chance my card is a club? Because there are 13 clubs, right? What's the chance my card is a red club? Because there are no red cards in the set of clubs. There are no clubs in the set of red cards. We're exactly in this situation. Now, if that intersection is empty, that means that the chance of being in that intersection is zero. And that means that I can write this. The chance of A or B, the chance of A plus the chance of B minus the intersection. But the intersection is zero. There's nothing in the intersection. So I would add, but I can only add when there's no overlap. If there's any overlap at all, I have to remember to subtract the overlap. Questions? Because I'm such a geek, my wife bought me a t-shirt. And it's got a picture that looks exactly like the Venn diagram that we were looking at earlier. And it says, I don't often make diagrams, but then I do. I don't know. A set of events is collectively exhausting if those events make up the whole sample space. Wait a minute, I want to call them E for event. So if I ask, chance your card is red or black, well, there are 26 red cards, 26 black cards. There's no overlap. Those two events are disjoint. We have 26 plus 26, 52 out of 52. That's something that had to happen. That's every possibility. The card's either red or black. All you get. Now, those two events happen to not only be collectively exhausting, they also happen to be disjoint because there's no overlap between red and black. But that's not required. We can have groups that do have overlap that are still collectively exhausting. It's nicer if they don't have any overlap, collectively exhausting and mutually exclusive. Questions? So, one of the things that happens often is that I get some extra information as I work on my probabilities. And depending on what that extra information is, it might change my probabilities. We're going to write a vertical bar, and we're going to read this as the probability of A given B. So we're given this extra information. So what happens now is that I change my picture a little. Let me go back to my Venn diagram again. I've drawn them as non-disjoint because I don't know whether they're disjoint or not. This is the easier picture to start with. So, the probability of A given B. Let me give you an example. What is the chance you pick a card at random from this deck? That card is a heart. 13 out of 52. Hearts. Hearts are back here. There. Right? What's the chance you pick a card out of this deck and it's red? Okay. Shuffle, shuffle, shuffle. Pick card. Here's my card. What is the chance this card is a heart? If I tell you it's red. I've given you more information, haven't I? So what I'm now asking is what's the chance that this card is heart given? Say again. Why? Because I've changed my sample space. If I think of red cards, hearts, right? There are more reds than hearts. But what I'm now saying is you can't use any of this part. You can only use that part. So I've really, when I look at this probability of heart given red, I change the way I think of my universe. I'm no longer thinking in terms of the whole deck of cards. I'm only thinking in terms of the red cards. Well, there are only 26 red cards. So I can say, oh, well, this is now 13 out of 26 instead of 13 out of 52. But let me put that back in terms of these fractions. I'm going to be sneaky. And instead of writing this as 13 over 26, I'm going to write this as 13 out of 52 over 26 out of 52. Right, the out of 52s would cancel. But now I can see these are the probabilities up here. Oh. So here's a sneaky way of thinking about this in terms of probabilities of other things. But really, this is kind of rigged here. Because really what I should be asking is what's the chance that it's a heart and it's red? Because that would put me in this part, wouldn't it? I'm not allowed to use any of that bit. I can only use the part in the middle. This is really the probability of red and heart over probability of red. Because I need to be only looking at that comparison. How much of the red group is made up by heart and red? What's the overlap? So in general, what we write is the probability of A given B is the probability of A and B over the probability of B. Often, we'll actually know this information more than we'll know this information. So we often write this formula a little bit differently, and we write the probability of A and B is the probability of A given B times the probability of B. Because it's almost always easier to calculate conditional probabilities first. Questions? Page 163. About video on demand here. Talks about 70% of new movies were available as video on demand within 2 weeks of their release. Half of them were released on TV pay-per-view. What is the joint probability, the and, that a movie was available as video on demand within 2 weeks as TV pay-per-view? So I want to know the chance of V and T. But what I was given here was 0.7. That 0.7 is the chance of being released as video on demand, period. This 50% is the chance of being released as TV pay-per-view of those movies, given that it was released as video on demand. So this is a conditional probability. That sentence right there is what tells me this is conditional. So that 0.5 is the chance of being TV pay-per-view, given that it was released on video on demand. So I got a different conditional rather than joint. So to get the joint, I have to multiply. There's really only a 35% chance that any new movie will be available in video on demand and as TV pay-per-view as opposed to some conditional streaming setup. Multiplying those, I get 35%. Question. Again, we want to read our words in the problem that's given to us. We want to understand what they're telling us carefully. Here's another one. Problem 23 here. 62% of freshmen are taking a foreign language course. Of the students taking a foreign language, 80% are taking Spanish. What is the problem that a randomly selected freshman is taking Spanish? So I take a freshman student. What's the chance they are taking Spanish? Let me interpret these two numbers. The 62%. What's that mean? That sentence says 62% of freshmen are taking a foreign language course. So the probability of a foreign language is 0.62. How did you come about that?
I just multiplied 0.62 by 0.8.
Okay, so my question is that 0.8.
Okay.
How do I know that's a conditional? Which would be the way I would use this result, right? So 80% of freshmen take Spanish, given that they are in a foreign language at all. And notice the order is important. So in this particular problem number 23, I can read this as the probability that a student is in a foreign language and the probability that if they are in a foreign language, then that foreign language is Spanish. These two have to match. Notice the B matching the B there. So the order in which I get that is important. Being a freshman in a foreign language and being in Spanish is exactly the product of those two. You said it was 496?
Yeah.
There we go. Now, the first time I read this problem, I read it wrong. I read that second sentence as students taking foreign languages being Spanish as the intersection. So I read that as this part, not as this part. So what happened? When I went to try and solve, I ended up with 0.8 divided by 0.62. But 0.8 divided by 0.62 is bigger than 1. I knew something was wrong. My probability can't be bigger than 100%. Questions? By the way, the red card I picked actually wasn't a heart. But in general, knowing the color of the card we picked gave us a little bit more information and changed our probability. I want to name this idea. If the chance of A is not the same as the chance of A given B. So if getting that extra information changes something, then we have dependent events. They somehow depend on each other. Now, this is not cause and effect. The fact that I know B didn't cause the probability of A to change. It didn't cause A. It caused the probability of A to change. So there was no way that cause and effect, hey, this is a red card, what's the chance it's a heart, is the fact that I told you red didn't cause it to be a heart or not a heart. Just that I could have a different result. In the same way, the probability of getting lung cancer is non-zero, right? It's a horrible statement. The probability of getting lung cancer, given that you smoke, is higher. Does smoking cause lung cancer? I'm going to leave that to the medical people, but it's a lot more common in people who smoke. But there have been people who've never smoked a day in their entire life who get lung cancer. That's okay. It's not a guaranteed cause. It is connected. It changes the probability. That's what dependent here means. It changes our probability. But what if it doesn't change my probability? What if knowing this extra information didn't tell you anything? Now, again, the order matters. If I were thinking about the probability of B, I'd have to think about comparing that to the probability of B given A. So, an example. Pick a card, roll a die. You roll the die first, you pick a card. What's the chance your card is red? What's the chance your card is red? If I tell you you rolled a 3, doesn't make a difference, right? There's nothing this die can do to affect these cards. Those are independent events. Roulette. You know the game roulette? Big wheel with all the numbers in it. 1 through 18, 1 through 36. 18 of them are red, 18 of them are black. And if you bet money on red or black, it's a 1-to-1 bet. You bet $1, if it comes up red, you get $1. You bet $1 on black, it comes up black, you get $1. In addition to the one you laid down, so you double your money. What's the chance it's going to come up red, given the last one came up red? The little ball in the roulette wheel doesn't remember what color it was just on, so each turn of the wheel is independent of the previous one. Turns out there are 2 more spots on a roulette wheel that are not black and not red. They're green, 0 and 00. And those numbers belong to the house. You can bet on them directly, but when you bet on red and black, you're actually betting out of 38 numbers, not out of 36. So when you spin and bet on red, you're betting 18 out of 38, not 18 out of 36. But the fact that it is independent means I can ask, what's the chance I'm gonna get a red result twice in a row. Here's your dice. Roll it. What's the chance you get a 3? Roll it twice. What's the chance you get a 3 twice? If these events are independent, I'm asking what's the chance you got a 3 on the first roll? And what's the chance you got a 3 on the second roll, given that you got a 3 on the first roll? There's a conditional probability in there, isn't there? But we know that to do conditional probabilities, we multiply. But in that case, they're independent. So the chance of A is the same as the chance of A given B, which means instead of using this version of the rule, I can replace this with just the probability of A. So I rolled a 3 first time, and the second time, the die has no memory. So the chance of rolling a 3 is 1 in 6 times 1 in 6, which is 1 out of 36. Very different than 2 out of 12. Three on the first one, 3 on the first one, and on the second, three on the second one, given 3 on the first one. But because these are independent events, I can replace the second one with the same probability. If I have more than one independent event, I'm going to roll not one of these dice, not twice. I'm going to roll it 5 times. What's the chance I get all of them to be 3s? Let's see, should go there. Sorry. Oh, wait a minute. That should be first 3, second 3, third 3, fourth 3, fifth 3. A very small number. Please note, that's the same as if I asked the question, what's the chance of rolling a 3 on each of 5 separate dice? So instead of doing this as 1 die 5 times, I could do it as 5 dice. There's a game with 5 dice that does it, Yahtzee, right? Play exactly this game when you play Yahtzee. As a matter of fact, no matter how many independent events I have, independent events just multiply. How many of you have your data stored in the cloud? On what service? Is it in your Google Drive? Is it on OneDrive? What are you using? Okay. Okay, but if you've got stuff in iCloud, then that's on an iCloud server, right? Let me make an assumption. I'm going to assume that the server your data is on is 99% not going to crash. Everything will be fine 99% of the time. If there's only a 1% chance of a crash, then every 100 times you get on iCloud, one of them I should lose something, right? That sucks. Apple knows this. So what do? They take your data and they don't just make one copy of it. Your data is not on iCloud in one server. It's in more than one server. So let's suppose it's in two servers. If it's in two servers, then when you ask iCloud for your information, it could look on either of those. What's the chance that both crash? Your data is on an iCloud server in Greensburg and another one in Pittsburgh. Or maybe it's on the one in Pittsburgh and the one in Sacramento, California. I don't know. But your data is on two servers. What's the chance your data is gone? Assuming both servers are equally good. Each one only has a 1% chance of crashing. Why? Right. So it would be probability of crash on server 1 times the probability of a crash on server 2. One out of 10,000. Which means what's the chance your data is fine? Right. The chance of not crashed, that's a complement. That's 1 minus the chance of a crash. %99.99%. Okay. Is that reliable enough? A lot of businesses will answer this question with no. Anybody ever heard the phrase 5 nines or 6 nines? For data reliability in particular, all of you using data servers and online services. 5 nines means I want 0.99999. 6 nines adds one more. Well, in order for me to get to 6 nines, I need my data on 3 different servers. I need to have it into 3 different places. If each server is 99%. But I go down to Best Buy and I say, give me a server rack. And I look in the documentation and that server rack isn't 99%, it's 95%. So as each probability changes, I have to put my stuff on more and more and more data centers. That's why your data doesn't just exist in one place in the cloud. It exists in 5 or 6. So if any one of those access points goes down, I didn't lose your stuff. Redundant business systems for billing, client records, sensitive information. That's the whole reason these data centers exist. So we don't lose stuff. There's an example on page 100 and I wrote it down, 168. When I'm dealing with more than one probability, one of the easiest things to look at, especially in multivariate data, is to make a contingency table. A contingency table is a table made up of frequencies or probabilities in various rows and columns across several categories. So I'm going to steal this from page 170, example 5.3, where we look at a bunch of MBA students and we ask, which type of program are they in? And there are three types. M1 is a full-time program, M2 is a part-time program, and M3 is an executive program. And then we did a survey and asked for their engagement level. How often are they on Canvas? How often are they in the modules that we created? How often are they watching the videos? How often are they doing the live exercises and accessing the data sets? And then we surveyed 360 people. We looked at the classes and we pulled up 360 records. And low, medium, and high, they called these E1 through E3. And we found 210 full-timers had low engagement, 64 part-timers had low engagement, 6 of the executives, 20, 17, and 16 for medium engagement, 5, 7, and 15. Now, to make a contingency table useful, I need to sum all the rows and all the columns, and then I need to sum both of those. So we'll sum downwards. 280 students had low engagement, 53 had medium engagement, 27 had high. There are 235 students in the full-time program, 88 in the part-time, and 37 in the executive. And as I said earlier, those add up to 360. Now I want to start looking at a bunch of these probabilities that I can get directly from this table, but I can generate joint probabilities. I can generate conditional probabilities. I can generate lots of probabilities given this information, but I've run up against the clock. So we'll pick this up next time. But next time, it's Monday because Friday is. I'm going to post the homework key or homework 4 right now, so you have it to work with, and then I will talk to you all more about this on Monday. Have a wonderful weekend. Well, have a wonderful day. I'll see you all Friday.